So there are 10 properties of the cross product we want to talk about, but they're separated into two blocks. One's more algebraic and the other one's more geometric. So we're going to go through these algebraic properties first, and then we'll move to the geometric. So if we have three vectors, u, v, and w, and any scalar c, it even could be 0, then something we've discussed in previous section is that u cross v is the negative of v cross u. So if you, unlike the dot product, if you swap the order of crossing, you're going to get a different result. It's related, but it's not exactly the same. The second one is a lot like how the dot product behaved. You have u cross v plus w. So if I have two vectors added together and I take the cross product with u, I could take the cross product with those separately. Or more likely, you're going to have two cross products and you might be able to simplify that and perform this addition before performing a cross product. It's all about whatever's convenient. The third one is that if I have a scalar times a cross product, I can distribute the scalar to either one of these. Or, again, more likely, you may actually have multiple scalars on both, and it may be easier to pull that scalar out, compute the cross product, and then multiply the scalar back in. That is a more likely scenario. The fourth scenario is kind of intuitive. If you cross a vector with the 0 vector, you're going to get the 0 vector. And if you think about that, the way that the cross product is constructed, you're multiplying components. Well, if you always are multiplying by 0, you're just going to get 0. The fifth one's a little less intuitive. Remember, for a dot product, u dot u is the magnitude of u squared. But for a cross product, it's actually the 0 vector. And that follows from the nature of how the cross product is constructed. And finally, we have what's called a triple scalar product, which is not only a dot product, but a cross product. So if I have a u dot v cross w, I could instead do u cross v and dot that with w. This doesn't come up a lot until it does. It's one of those kind of things that you don't see a lot, but when you do see it, it's very important. And we'll reference that as things go on. So that's the idea of these algebraic properties. Just the sort of algebra, multiplying, adding kind of stuff. But the geometric ones are sort of the more intuitive, sort of the think about the actual spatial properties of u and v. The first one is that the cross product is orthogonal to both the generating vectors. And we've already kind of discussed that already, and we can show that directly. The second one is how we figure out what the magnitude is. So the magnitude of u cross v is the magnitude of each of the vectors times sine of the angle between them. Notice that's very close to the way the dot product is, but the dot product is the cosine of the angle between them. The third one is that the cross product will only be 0 if they're parallel. So if they're parallel, you know their cross product is 0, or if their cross product is 0, you know they're parallel. Now, it's important to note, in this particular case, they're both not the 0 vector, so don't think about this particular case. Think about this really as this case and this case put together, because if they're parallel, then one is a scalar times the other, and then you just have this case with that scalar out front. So this is the case where if they're parallel, they're not going to be able to cross each other. And if you think of that back to that ratchet example, there's really no, if the force is happening along the lever arm, nothing happens. You're not actually moving the lever arm. No resulting force is happening. And finally, there's this geometric representation that the magnitude of the cross product is actually related to the area of a parallelogram that has u and v as adjacent sides. So you could think of that as if I had u and v and then those were also u and v, this would form a parallelogram, and we could find the area of that parallelogram by taking the magnitude of u cross v. And of course, in the case where it's a square, U and V are perfectly orthogonal already. The angle between them is 90 degrees. So that would be the magnitude of the side. So really not just a square, but a rectangle. Any rectangle is, height times width, which is that, and the sine is the angle there. So there's a lot of geometric relationship of what the cross product gives us versus the area. And those are the properties of the cross product.